Hello everybody, today we will be going over a optimization problem at the IB Masteries level. So we have a company that sells fruit juices in cylindrical cans and each of which has a volume of 340 centimeters cubed. The surface area of a can is 8 centimeters squared and is given by the formula blah blah blah, where r is the radius of the can in centimeters. Okay, and so of course to reduce the cost of a can, its surface area must be minimized because then you spend less material creating the can itself. So for part A, we need to find dA over dr. Now what the heck does this even mean in the first place? This makes reference to you will take the derivative in your function A of the variable r. Okay? So most of the time, you actually see this in the form like this. You see a dy over dx, which again is in your function y, you're going to take the derivative of x, which is also seen very commonly like this in f of x. Okay, so that's just a quick reminder of how some of this language is used. Okay, so to find dA over dr, we can do the derivative of this guy here, but before we jump into the dA over dr or the first derivative, it's important to rewrite this problem a little bit. Okay, I mean rewrite the expression a little bit. Why? Well, because we have r in the bottom, okay? And taking the derivative of a variable that's on the bottom, unless if you've done this a bunch of times, can get very confusing. So what I suggest you do is that anytime you have a variable on the bottom, you want to put them up top. So to put r up top and make this easier to do the derivative of, it would end up looking like this. We have 680 times r to the power of negative 1. Okay, so if I have, for example, 2 squared, this is 4. If I have 2 to the power of 1, this is 2. 2 to the power of 0 is 1. And 2 to the power of negative 1 is going to be 1 over 2. And 2 to the power of negative 2 is going to be 1 over 4. And so keeping that idea of how the negatives work, which is essentially putting just the exponent, the number on the bottom, using this idea here, we can do this trick legally without changing the function in any major way, just how it looks like. Okay, so now that we're at this position, it's much easier to do the derivative of dA over dr, and it's going to look like this. For the first one, because this is all exponent derivative, we're going to take the 2, multiply it with whatever is in front of it, so it's going to be 2 times 2 is 4, pi is not going to change, and my exponent is going to be subtracted 1, so it's going to be 2 minus 1, which is just 1 up here. Okay, we have this subtracted to 680. Why is it subtracted? Because this times 1 is multiplying to the 680 over here, and my my exponent is going to have a minus 1 to it as well, so we're going to have minus 2 up here. So this is part A, this is the derivative of dA over dr. Now for part B, we need to calculate the value of r that minimizes the surface area of a can. And so anytime you want to work with minimizing or optimizing any sort of optimization, you will always equal this to 0. Okay, and I will explain at the end of the video why we equal it to 0. But for now, just roll with it. So here we're going to have 4 pi r minus 680 r to the power negative 2 equals 0, right? And so how exactly can we solve this? We are find the value of r, which gives us 0. And what I think is the easiest way to solve this is by going over to your calculator and going ahead, going to your y equals, putting in the whole function into it, and then doing calc intersect. And I have a video that goes in depth in how that works, but I do really think this is the fastest way to solve it. And once we do calc intersect, we end up with an R value of 3.7823. Now remember, if you put this as your answer in the test, you're going to make sure that you write, I put this left side for y1, I put this right side for y2. I did calc intersect, and you get full credit. Another way to solve it without using calc intersect is noticing that if I rewrite this function here, we're going to end up with r squared on the bottom, right? And so in a certain way, if I want to get rid of this r squared, I just need to multiply everything by r squared, right? And so if I go ahead and do that, I multiply everything by r squared, on the right side, I still end up with 0, but on the left side, my first element is going to be 4 pi r cubed, and my second element is only going to be 680. So now suddenly this is a much more approachable problem, because I'm going to do plus 680 to both sides to get rid of this guy here, and end up with 4 pi r cubed equals 680. So here, since we want to get r alone, the next important step would probably just be to divide by 4 pi. So I'm going to go ahead and divide by 4 pi. Gets rid of that here. We end up with r cubed being equal to 680 over 4 pi. And I'm going to do the square root to the power of 3 here. And so if I do that, I'm going to get rid of the exponent 3 and end up finally with r being equal to square root with exponent 3 of 680 divided by 4 pi. Okay, so both of these are valid answers. If you put this into your calculator, actually, we get the same answer that we did doing the other, solving it the other way. Okay, so that I just wanted to show you another way to get the same answer, because that's always important. So that is how you solve this problem. Now I will explain why you equal it to 0 real quick, but really this is all you need to know. So why do we equal to 0? Well, because usually when we are dealing with a function of f of x, for example, x and f of x, and we have our set of points, right? Like, I don't know, 1 and 0, 2 and 1, 3 and 2, whatever. These are sets of points, right? These are a bunch of x, y's. However, when we go ahead and have the first derivative, it's not a set of point anymore, okay? This is actually, if I plug in, for example, 3 here, this gives me, I don't know, I'm making it up, right? This gives me 6. This is actually saying that in your x of 3, so in your set of points where we have a 3 and something, you will have a slope of 6. This suddenly turns into slope when we have it in this, when we have it in a derivative form, right? And so why does it matter that we have a slope of 0? Well, because when we're dealing with quadratics, as we can see here, there's a squared over there. When we're dealing with quadratics and things like this, anytime your slope is 0, you will be either at a minimum or a maximum, because the slope of this line here is 0, and the slope of this line here is 0, and you will find the x value that gives you that slope of 0, and that will be your optimization point, right? Just to talk a little bit more about the slope of this line here is probably like, I don't know, -3. Here goes to -2, and eventually you reach slope of 0. Okay, so when you're forcing the function to be a slope of 0, which is what we do here, you are forcing the function to give you the x value, or in other words, the set of points that give you the minimum or maximum, which is the same as the optimization, and in this case, what minimizes the surface area of the can. So that is a deeper explanation of why we equal it to 0, but always just remember to do it because it's a very important step. Also, very important that you make sure that you put your units in this exercise. Notice that it is worth 3 points up top and up bottom for parts A and B. So clearly we need to put additional information, and in this case, putting your units is literally a whole point. So careful with that. So that is how you solve this problem, and I hope it helped.